Hello, I'm Miji Shizuka. I'm from Group E, and today our topic is the advantage of honeycomb structure and unification of conditions and problems in remote experiments. First, let me introduce honeycomb structure. It takes its name from its visual resemblance to bee's honeycomb, a hexagonal sheet structure. Honeycomb structure has been admired for a long time. It has given scientists countless ideas and made a significant contribution in a long history. For example, the cellular network system is the base of 4G. We can say that we have been surrounded by honeycomb structure. The greatest feature of honeycomb structure is minimizing the amount of used material while providing high intensity. The objects in Figure 1, 2, and 3 are examples of utilizing this special feature. As we marveled at its power, we wondered whether honeycomb structure really is as good as it is said, whether other shapes could do better, and whether the area of shapes can be affected. Since the strength of the planar packed structure is higher than that of the non-planar charged structure, we conducted an experiment that measured the strength of the triangular, quadrilateral, and hexagonal structures with different per area. Now, we'll move to the next section, which will be presented by my colleague, Mr. Ozaki. Please.
I'm Shota Ozaki. We devised it to be used so that everyone can experiment remotely under the same conditions. Also, when creating the figure, the size of the surface of decided in advance under the same conditions. How to create is as shown in the poster. The experiment is performed as shown in figure 4, 5, and 6. In experiment 1, the results are compared from the viewpoint of the load capacity per area seen from above. And in experiment 2, the size of each figure used in experiment 1 is large. The results were compared when the height was changed. By doing so, it became clear how the honeycomb structure is superior to other figures. Next part is experiment 1. Presenter is Mr. Mizuno.
Thank you for great presentation, Mr. Ozaki. I am Takeshi Mizuno. I talk about result of experiment 1. We check the 3 data. They are load capacity from the weight, the area when 8 figures were lined up, and the amount of the material used to make them. Then we calculated using these data and evaluated 3 structures from the following 3 indicators. Indicator 1 is load capacity per area. If a structure has most number in this indicator, we thought it is the strongest structure which can be made of lowest amounts of material. Indicator 2 is load capacity per material. If a structure has most number in this indicator, we thought it is strongest structure when figures have same space. Indicator 3 is area per material. If a structure has most number in this indicator, we thought it is the widest structure which can be made of lowest amounts of material. I summarized them in this table. Please look at the table 1 below. From these results, it can be seen that the triangle is the best in load capacity per area, indicator 1, and the hexagon is the best in load capacity per material and area per material, indicator 2 and 3. In other words, it turned out the triangle is strongest structure in the same area. The hexagon can make a strong structure with the same amount of material, and it is a structure that makes a wider area. Next part is experiment 2. I'd like to turn things over to Mr. Tanaka.
Thank you, Mr. Mizuno. I am Soda Tanaka. In experiment 1, the hexagon was found to be superior in that strength per material and area per material. Experiment 2, the change of scale was examined. It is experiment how the load capacity changed by the various scale material. It is also checked whether there is a variation depending on the figure. We have two predications. Predication 1, the hexagon stability is the best. Predication 2, the more material area expands, the more structure durability becomes weak. Please look at figure 7. Figure 7 shows the result of experiment 2. There was no difference in the change by the figure. If I must say, the hexagon there is a difference in the rate of decrease. Predication 2 is correct. The durability of the material decreased as the area increased. And we consider the data in the new viewpoint. The data shows that durability decreased as the area of material increased. In addition, the area will be expanded. In other words, the increase in area equals the decrease in durability. Triangle, square, and hexagon have different areas. We cannot compare them simply. Therefore, it was shown by the approximate curve by the calculate. We calculate as follows. Step 1. Calculate weight per area. These numeral values are obtained by the strength data in experiment 2 by structure area. Step 2. List by area per shape. 3. Plot and compare approximate curve. Please look at figure 8. These treatments have shown that hexagons are strong any scale of intensity per area. In experiment 1, we compare 2 points. Therefore, we mistake that triangle is superior hexagon in terms of strength per area. The next section will be presented by Ms. Suzuki.
Thank you, Mr. Tanaka. Finally, I will describe the conclusion of this project. From the result of experiment 1, it was found that the hexagonal shape is superior in load capacity per area and load capacity per material to other figures. Therefore, it was confirmed that one of the reasons why the hexagon is used for the structure of an airplane is that it is excellent in that the strength can be efficiently increased with a small amount of material. From the result of experiment 2, it was confirmed that the durability decreases as the area of the material increases. As a result of the calculation based on this, it was shown that the hexagon has a high strength per area at any scale. Therefore, It was confirmed that one of the reasons why hexagons are often used in life is that they have excellent durability even in large buildings or small furniture. For these reasons, which we got through this project, we found that hexagons are used everywhere. Thank you for your listening.